Hi everyone, welcome back to Minding the Mind. I am Dr. Derick Lindquist. I am the Dean of the Jindal School of Psychology and Counseling, and I'm really happy to have you with us today. So in our last two episodes, we talked about action potentials. Today, we're going to talk about synaptic transmission. Now again, the goal here is to provide just a little bit more information. Understanding this process of electrochemical signaling will really be key in some of the forthcoming episodes. So again, it's worth taking a little bit of additional time to understand this in more detail. So electrochemical signaling. We already talked about the electrical component. That's the action potential. It starts at the axon helix, it travels down the axon, and ultimately it invades the axon terminal. The chemical part is the release of neurotransmitter. You can see that here in this beautiful image. And if we go back, you can actually see an action potential occurring in this real live image of a bunch of dendrites and their synapses. So today we really want to understand what are the mechanisms that underlie the release of neurotransmitter from the axon terminal. Well, first, we need to understand a little bit of terminology. So here we have two neurons. They're connected via a synapse. So on the left here, we have the presynaptic. Right? This is the one where the axon travels down. The axon terminal, the presynaptic terminal, now makes contact with the postsynaptic neuron. And on the dendrite, we have a spine, this little protrusion that sticks out here. Okay? So that opposing terminal, we call it the postsynaptic terminal. Okay? Presynaptic is the axon, postsynaptic is the dendritic spine. So when that action potential arrives in the axon terminal, it leads to the activation of voltage-gated calcium channels. Now, in the last couple episodes when we talked about action potentials, right, we talked about voltage-gated channels. Calcium is a positive ion. There's a lot more outside than inside the neuron. The inside of the neuron is electrically negative. So when that voltage-gated calcium channel opens, we have calcium quickly flow into the axon terminal. The effect of that is it will actually trigger these cascading effects that lead to the release of neurotransmitter. Interestingly, if you actually look here, you can see that we have a single synapse, and you can actually see a little bit of that calcium flowing in. So what does the calcium do? Calcium acts on these synaptic vesicles. You can think of a synaptic vesicle as just a big balloon, right? It's like a hollow circle. So that synaptic vesicle is filled with neurotransmitter. Here in blue, over there in red. The vesicle itself is made of the same membrane as the neuronal membrane itself. So when calcium comes in, that vesicle will move downward. It docks with the presynaptic terminal. And ultimately, that vesicle will fuse with the membrane, spilling its contents out into the synaptic cleft. Okay, so over here on the left, you can actually see an image of this. We have the vesicle initially, and it will then fuse with the neuronal membrane and again, expel its contents into the synapse. So you can see that here with all the pink vesicles and the neurotransmitter in red. This process is called exocytosis. Exocytosis is the mechanism whereby the action potential leads to the release of neurotransmitter. Okay? So these are actual images of neurons. These are electron microscopy images. Over here on the left, you can see some calcium channels. Over here on the right, you can actually see vesicles, that's the circles, and you can see them fusing with the membrane itself. This leads to exocytosis and the release of our neurotransmitter. Okay? And once again, the reason this can happen is because the vesicles are made of the same compound, this lipid bilayer, as the neuronal membrane itself. So it's very easy for it to fuse with the membrane. And once that neurotransmitter has been released, we can then pinch off a new vesicle from that presynaptic terminal. This is known as endocytosis. So in this manner, we release our neurotransmitter and then we pinch off a new vesicle. You can see that down here in the electron microscopy image. And that new vesicle is now ready to be refilled we can put new transmitter inside, and we repeat the process all over again when a new action potential invades the terminal, leading to calcium influx, vesicle docking, and ultimately fusion and exocytosis. So you can see this whole process spelled out for you. Each time an action potential occurs, this occurs very, very rapidly. Within a millisecond, that neurotransmitter now is released within the synaptic cleft itself. Now, I've been saying neurotransmitter, but what is a neurotransmitter? Well, to define it, we really have these three criteria that must be met. One, the chemical, i.e. the neurotransmitter, must be synthesized in the neuron or otherwise be present in it. Two, when the neuron is active, that is, an action potential occurs, the chemical must be released and produce a response in the target neuron, the opposing neuron, the postsynaptic terminal. And finally, a mechanism must exist for removing the chemical from its site of action, that is, from within the synaptic cleft. As we're going to see, these classical neurotransmitters that we are familiar with do in fact meet all three of these criteria. So here's an example, right? Over on the left, I'm showing you a whole bunch of names. Some of these you are probably familiar with. So the first are called small molecule neurotransmitters. And the chemical precursors are usually derived from your diet, that is, the nutrients that you take into your body. So again, we have serotonin, norepinephrine, dopamine, acetylcholine, right? We've kind of mentioned many of these in past episodes. We also have glutamate and GABA. Glutamate is considered the primary excitatory neurotransmitter in the brain. GABA is the primary inhibitory neurotransmitter. So in the examples that I just showed you, we can have any of these neurotransmitters being released. And beyond this, we also have endorphins, right? So endorphins are released when you get that runner's high, for instance. Serotonin involved in mood, noradrenaline involved in concentration. So again, I think most people are probably familiar with many of these names for neurotransmitters. Now, interestingly, when we actually look in the brain, what we find is that the cell bodies, the neuronal bodies, are localized to particular locations within the brain. You can see that here for dopamine neurons in purple, and above you can see that for acetylcholine neurons in the big red circle. Okay? So this is where the cell bodies live. But those cell bodies, those neurons, have axons that can then be relayed or projected to various other areas within the brain itself. Through this mechanism, dopamine neurons can release dopamine throughout virtually the entirety of the brain. The same is true for acetylcholine, noradrenaline, and for the serotonin system. Okay? So this is a mechanism whereby when different things happen to you, right, it leads to the release of these neurotransmitters. An action potential occurs, and ultimately neurotransmitter is released. Now, beyond these classical small molecule neurotransmitters, we have what are called neuropeptides. So this includes insulin, vasopressin, oxytocin. Again, this last one some of you might be familiar with, sometimes called the love hormone or the trust hormone. So we know, for instance, that oxytocin is released via uterine contractions during childbirth. When the mother nurses her baby, oxytocin is transmitted to the baby. We believe that it facilitates social bonding between the mother and her child. And we even see this in males. So if you're in a committed relationship, it's the release of oxytocin in both the man and the woman that, again, promotes that social bonding or that social binding that we see between these two individuals. Finally, perhaps strangely, we actually have gases in our brain as well. So one of these is nitric oxide. Nitric oxide can be synthesized and released directly within the brain. And nitric oxide acts as what we call a vasodilator. Vaso is blood vessels, to dilate. So nitric oxide has the effect of increasing blood flow within the brain. Okay? The classic example of this, of course, is Viagra. Viagra is also a vasodilator and increases blood flow to the genitals in this case. Now, step 5. We've now released neurotransmitter into the synaptic cleft. The primary purpose of that is to then bind to and activate postsynaptic receptors. That is, receptors that are found on the postsynaptic terminal. This is a fairly complicated story. We're going to come back and talk to you about this in a little bit. So right now, let me skip ahead and talk about the final step here. Once that neurotransmitter is released, we need some way to remove it, to clear it from the synapse. Because ultimately, each time an action potential occurs, we want new neurotransmitter to be released and bind to those postsynaptic receptors. That means very quickly we release that neurotransmitter and then we get rid of it. Okay? This can occur in three ways. One is through diffusion. Okay? All the neurotransmitter here in red is released into the synapse, and then it just kind of spills away. It diffuses away where it's no longer activating those postsynaptic receptors. Secondly, we can inactivate. So acetylcholine, for instance, is made up of two compounds, acetyl and choline. Once it's released into the synaptic cleft, an enzyme can come in and it can essentially break acetylcholine in half. It inactivates it. It's no longer capable of activating the postsynaptic receptors. And then finally, we can take that neurotransmitter back up into the presynaptic terminal. This is done through a channel called a transporter. You can see an example here with the arrow pointing inward. And so a transporter allows that neurotransmitter to be released, to be sucked back up into the presynaptic terminal, where it then can be refilled into a new vesicle and reutilized and used over once again. So the transporter here in blue, you can see once the neurotransmitter, the green molecule is released, it can be taken back up. And we can see the same thing in the little cartoon over here on the left. So this is it. Action potential occurs, the electrical part, which leads to the release of a chemical neurotransmitter, and this is how communication or signaling occurs within the brain. So when I see you again, we'll talk about this further. Thank you very much. I look forward to seeing you then.